Okay, so there's two ways that we can define a sequence. One is an explicit definition and the other one's a recursive definition. And for each of those, our sequence could either be arithmetic or geometric. It doesn't have to be, one applies to one and one applies to the other. So you can have both arithmetic geometric sequences that are written down explicitly or written down recursively. The difference is that a explicit definition, so I'll just write down a sequence here, t of n, I'll just say equals 3n plus 2. I don't know. I just made that up. This is an explicit definition, so if I say put the number 1 in when n equals 1, right, when 1 hits in there, it gives me the first term of the sequence. 3 times 1 is 3 plus 2 is 5, so 5 is my first term. When I put in a 2, I get 6, and 6 plus 2 is 8. So it increased by 3. If I put in another, if I want so that's the first term, the second term. If I want to do the third term, 3 times 3 is 9, plus 2 is 11, 8, 9, 10, 11. So I can see that the terms are increasing by 3 each time. And I can also see that my zeroth term, if I was go back and look at it, is the number 2. So this is an explicit definition for a sequence. Now I could also write the recursive definition for this exact same sequence. And the recursive definition has two parts, right? We have to say where the sequence begins. We have to list that. And then we have to say how do we get to other terms in the sequence. So for the exact same sequence, right, that's the explicit definition. The recursive definition looks like this. I would say t of n, and I can use a subscript. The first term is the number 5. Okay, I didn't want to write t of n. I want to write t of 1. So there I am saying the first term is 5. Now I could just have as easily given the zeroth term. It doesn't really matter which one. We usually either give the first or second, but I could say the zeroth term is 2. Okay, and that's just fine. If the zeroth term is 2, or you could say the first term is the number 5. And then what you say is, how do you get to other terms? So I could say, this is the notation. I could say t of n plus 1. This is read the next term in the sequence, right? Here's the term I'm at. Right, if I'm starting at 1. Here's the term I'm at, and it says, in order to get to the next term in the sequence, you take the term that you are at, and you add 3 more, right? So in order to get to this is like if this is the t of n, right? It's 1. In order to get to the next one, in order to get to the one that's after t of n, in order to get to this one, you just take this term that you're at, 5, and add 3 more. So if I wanted to know, so if I look at this, if this says, if I want to know what the, for example, third term is, if I want to know the third term, it says in order to get the third term, right, take the second term and add 3 to it. So the third term is the second term, 8, plus 3 more, which is 11. Okay, so together, these form the recursive definition of this arithmetic sequence. They tell me where to start and what to do each time. It says I keep adding. You'll notice in the explicit form, it's telling me, yeah, my zeroth term is the number 2, right? And just keep adding additional 3s. And you see that repeated addition is being shown with multiplication, right? So as n increases, it just adds another 3 to this. So let's go and look at our particular problem here. It says write the explicit rule. So the explicit one, that's the one where you just plug in n and it tells you exactly what it is for this sequence. And if I look at this sequence from 8 to 12 is a jump of 4, right? So I'm adding 4. 12 plus 4, it gives me the 16, and 16 plus 4 makes me land at 20. So each time I'm adding 4 in this sequence. So I know that I'm going to have a 4 times n, right? Because I showed this repeated addition with multiplication, and I'm going to say the t of n, the value at any particular place in this sequence is equal to 4n, and then I have to do one more thing. I have to include the zeroth term, and you can see my first term is 8, and if I need to back up to the zeroth term, I'm just going to, instead of adding 4, I'm going to subtract 4, and 8 minus 4 is 4. Now, I've done some things here, right? But the thing is how do I know this is right? How do I know this is actually the explicit rule? Well, if you look at it, when I put in that n is 1, this thing needs to give me 8. When I put in n is 2, it needs to give me 12. When I put in n is 3, it needs to give me 16. So I'm just reading these values here, right? When n is 4, it has to say 20. So I could just check a couple of these. If n is 4, you can see this becomes 4 times 4, which is 16, and 16 plus 4 is exactly 20. So it does exactly what it's supposed to do. When I plug in 4, it gives me 20. If I plug in, let's just check this one as a final check. When I plug in the number 2, 4 times 2 is 8. 8 plus 4 is 12. So when I plug in 2, right, it gives me 12, which is exactly the second value. So this is precisely the explicit rule for this sequence. So question 5, I'll just do them both in the same video here. In question 5, I've got another sequence. And to be honest, I don't have my answer key with me, but I can tell that the difference between these is not the same, right? I'm not subtracting the same value each time. So this is probably geometric. Let me grab a calculator. So what I'm going to check and see if there's a common ratio here. So I'm going to take a term, and in this case I'm going to take the number 72, and I'm going to divide it by the previous term. So 72 divided by 216, and when I do that, I recognize that as the number 1/3, and I can ask my calculator to kick it into a fraction if I want. So I've got 1/3 here. So let's see if that's the same ratio for the other two. I'm going to take 216 and I'm going to divide that by 648, and you can see I get exactly 1/3 again. So as I move forward, right, this is multiplying by the number 1/3. So I've got a common ratio. Therefore, this has to be a geometric sequence. So they're asking me for the recursive definition. Now, for convenience, I'm going to write the explicit definition, and then I'll use that maybe to help me build the recursive definition. I know that any particular value is going to equal my 0th term, which I don't know yet, times 1/3 to a power n. So I know there's something I have to put here, times, and then parentheses, 1/3 to the nth power. The question is, what's that? Well, in order to get the 0th term, I'm going to take this first term, and instead of multiplying by 1/3 to go forward, I'm going to divide 1/3 to back up. So I'll take the 648, and I'm just going to divide it by, let me go grab this 1/3 that's sitting here. That's kind of convenient. So 648 divided by 1/3, same thing as multiplying by 3, and I get 1,944. So this is the explicit rule, right? If I put in 2, it would give me 216. If I put in 3, it would give me 72. Well, don't want the explicit rule. I'm asked for the recursive definition, and I know there needs to be two things. And these are the two things. I'm going to put down that the first term is 648. There we go. And then I'm going to put down the recursive part. It says in order to get to the next term in the sequence, take the term that you're at. So that's just notation, right? The next term, the t of n plus 1 term, is the t of n term. And what do I do with it? I multiply that by 1/3. So I'm just going to multiply by 1/3 to get the next. Now, notice how this shakes out, right? In the recursive definition, I'm showing multiplying by 1/3. And in the explicit rule, right, it's 1/3 to the nth power. Now, if I look at this recursive definition, it says, hey, start with 648. Okay, I'll start with 648. And it says if you want to go to another term, just take that and multiply by 1/3. There it is. And when I do it, I get, ta-da, right? Times, I'm going to take 216, I'm going to multiply it by 1/3. And it's like, ta-da, there it is. Times 1 divided by 3 times 1/3, 24 times 1 divided by 3. Ta-da. times 1 divided by 3. That's going to give me 8/3. So there we go. That's both kind of a look at both the explicit way that we can write out sequence rules and the recursive definition. And again, it applies to both. We've looked at arithmetic sequences here and geometric sequences.